Good morning and welcome to Class 4 of Engineering Economics. Today we're going to cover sections 2.3 and 2.4 in your ebook. And these sections deal with gradient series, two different kinds, the arithmetic gradient and the geometric gradient. And they also deal with the shifting of the time of the cash flows. So we'll look at both of those sections, and hopefully you'll be able to see what's going on. So in equation 6, 2.6 right here, that's the algebraic equation for the present worth of an arithmetic gradient series. Now, an arithmetic gradient series has some specific requirements. The first is that in year one the cash flow is zero. That means for this to be a gradient series, an arithmetic gradient series, it has to have a cash flow of zero in year one, and then it increases by an amount we call capital G. So it could be $100 a period or $200 a period, whatever it increases by. It must increase by that same amount every period. Those are the two conditions, and we have an interest rate of I, and if this goes on for n periods, then this is the equation. We don't usually use the algebraic equations because we have the Engineering Economics Career app on our phones, and we also have Excel, and we also have the symbolic formula and the tables in the back of the book. So there's different ways to do it without actually calculating this, although you can calculate it, certainly. And so I'm going to use the symbolic formula first, and then I'll use the app to solve this problem. Now, the example problem that I'm going to look at says, and this is the symbolic formula, by the way, and these notes will be posted online along with this video. The present worth is equal to, actually, the algebraic form of that formula is P is equal to G, find P given G at rate I for n periods. Now, it turns out that most series that may contain an arithmetic gradient series do not start at zero. Start at zero. So what you have to do with that kind of a series is convert it. That's called a combined series, by the way. Convert it to a uniform series plus a gradient series. So here's the example. The cash flow below starts with a cash flow in year one at 400. So right away we know if it starts here at 400, it cannot be a gradient series, because a gradient series, an arithmetic gradient series has to start at zero. Okay, but then it says the series increases by $100 each year through the end of year 4. So that means that the next payment at time 2 would be $500, and the payment at time 3 would be $600 because it's going up by 100 a period, and finally the payment at time 4 would be $700. Now, we want to find the present worth of that series. And let's see, where's the interest rate? I'll get to the interest rate, I guess, on the next page. Okay, so what I'm going to do is cut off the $400 there, and what does the bottom part of these cash flows look like? Well, that looks like a uniform series that we studied in the last class. So I'm going to draw that down here as a uniform series, 400, 400, 400, 400. And then what am I left with then? That's a uniform series or an A series. What am I left with? I'm left with 0 here. So if I take this 400 from that 400, I'm left with nothing. But if I take this 400 from that 500, I'm left with $100. And if I take this 400 from that 600, I'm left with 200. And finally, if I take this 400 from that, I'm left with 300. So now I do have an arithmetic gradient series here, and I have a uniform series. So I'm going to find the value of this series at 10% interest. So what I have, again, is 2 series. I have a uniform series and an arithmetic gradient series that I partition this cash flow into. So we know from the last lecture how to find the present worth of a uniform series, and now we know how to find the present worth of a gradient series using this formula 2.7. That's the uniform series, that's the gradient series. We're going to find the present worth. So I can do this in a number of ways. I can calculate the values, or I can look them up in a table, or I can use the app. I'm going to go ahead and show you how to use the app, but you could just as well use the tables or do the calculations with the algebraic formula. So I'm going to take my cell phone, and I'm going to go to the Engineering Economics Career app, which I've downloaded and installed on my cell phone. And then I'm going to go to this middle button here in the bottom that says Calculate. And the first thing I want to do is calculate the present value of the uniform series, and that's the third option down, and it's P given A. So I click on that, and this shows me the formula that I'm using, and then it asks me for the interest rate, and I'm going to put it in as a percentage. That's 10. And then it asks me how many years. Well, how many years do I have in that uniform series? Recall, that's a 4-period series. So I'm going to put in 4 for N. And then it's going to ask me what is my annuity value, or the A value. And recall, that's 400. So I'm going to put in 400. And then I'm going to, whoops, I got one more 0 to get. And then I'm going to scroll up and tell it to calculate. And when it calculates, it returns me the value $1,267.94. So this, what I put here is $1,267.95. That I got from calculating. It doesn't matter. We're just going to keep dollar values anyway. And the next thing, the next digit over from the 94 is a 6, so that would round that up to 95. The next thing I want to do, though, is go back here and calculate the present value of that geometric series, arithmetic gradient series, which is right here. And now, how many periods are in this series? Well, even though the first payment is 0, there's still 4. And that's the way the formula is designed, okay? And so I'm going to go back in my app, press back button, and now I want the present value of a arithmetic gradient. And there's a P given G that is the 4th from the bottom. I press that. I still have the same interest rate, so I don't have to put anything in. I still have the number of periods, but my gradient value, G, is now 100. So I have to take that out and put in 100. And then I scroll up and tell it to calculate. And it returns me $437.81. So I put that number right here. And then again, going back to this equation 7, I add those two together to get the total present value. So the present value of this series, in other words, I took these $400 and I brought them back to here using P given A, was 1,200, and we'll call it 68 because we'll round off to the dollars. And then the present value of this series, bringing it back to the present time, was 438, again rounding off to dollar value. And if you add those together, you're going to get $1,705.76, which we would round off to $1,706, and that would be the sum there. So that's the way that would look. The formula that the algebraic formula for the present worth of the gradient series that I gave way back on the first page, this formula is only good if I is unequal to the interest rate. I'm sorry, I is the interest rate. Let's see. This is the algebraic formula for the present value. I'm sorry. We are converting, in this case, the gradient series to a uniform series. So this is the formula, equation 2.8, and the symbolic form of that is find A given G at interest rate I for n periods. I'm going to go back here and see if that's on my, as an option. It is. It's the next one down. That's the A given G. And if I clicked on that, I could convert the uniform series, the gradient series, the arithmetic gradient, to a uniform series. And basically, I do that down here. I said, suppose we wish to convert the cash flow in the previous example to a uniform series. So instead of converting this cash flow to a present value, which we did by taking the present value of this and the present value of this, we want to convert that to a uniform series. Well, this is already a uniform series, so all we have to do is get the uniform series equivalent to this series, the arithmetic gradient, and add it to the $400. So that's what I'm doing in the next section here. We use equation 2.9, which says the total value of the uniform series is the value of the uniform part, that's A1, that's $400, plus the gradient part converted to a uniform series, and that's obtained using equation 2.8, or the symbolic form. And so I go here and I say A total equals A1 plus G, A given G, IN. That's 400. The G is 100. A given G, this is 10% for 4 periods. And then if I plug that into my calculator here, the I is still 10%, the N is still 4, and the gradient is $100, and I press calculate, and it returns $138.11, and so I just have 138 plus 400, which is $538. So with this example, I've shown how to convert a combined series, one that it has an embedded gradient, arithmetic gradient, and it also has an embedded uniform series. So in the next section, we're going to cover the concept of a geometric series. A geometric series is a series that changes by a percentage or a fractional amount, which we call little g. So we use the symbol little g to represent how much a geometric series changes. We use the symbol capital G to represent how much a arithmetic series changes. And a geometric series is very different than an arithmetic series in that it functions almost like the future value of a present sum, 1 plus I to the n, only it's actually 1 plus I to the n minus 1. So it's not an I, it's a g. So the formula for the term number t, a sub t, is a sub t minus 1 times 1 plus little g. So, for example, in this case, we have a series that's increasing at the rate of 5%. So, little g as a fraction is 0.05, and so that's the way we would get the tth term would be multiplying the t minus 1 term times 1 plus 1.05, so 1 plus g. So the general formula for the tth term is a sub 1 times 1 plus g to the t minus 1, because you can the first term in the series is a1, so it's not taken to any power. It's actually, so the first term is to the one is to the zero's power, so the second term would be to the 1 power, and so on, so that the nth term would be to the n minus 1 power. And so this is the way a geometric gradient series works. And I say, note that for an arithmetic gradient series, the first cash flow, A1, must be 0. But for a geometric gradient series, the first cash flow, A1, cannot be 0, because if the first one is 0, then they're all going to be 0 if you execute this formula. So it's quite different, and so we have two formulas here for the present worth of a geometric gradient. Now, if g is unequal to I, then this is the formula that you use to get the present worth of a geometric gradient series. If g, notice this, that in the denominator here is I minus g. Well, if g and I are equal, then that denominator is going to go to 0. And this equation is going to blow up. So you can't divide by 0. So we have a separate formula when I equal g. That's equation 2.11. And it's a much simpler formula. P is equal to A1 times n over 1 plus I. The symbolic form for equation 210 or 211 is P is equal to A1, P given G at rate I for n periods. Now, if you want to find the future value of a geometric gradient series, this is the formula if I is unequal to G, and this is the formula if I is equal to G. So certainly, if you know the present value, you can get the future value simply by multiplying through by 1 plus I to the n. That much we learned in the previous class. So I'm going to give you an example problem now. The example problem says, on Juan's 26th birthday, he invested $8,000 in a retirement account. Each year thereafter, so let's put that $8,000 here, 26th birthday. right there, 25, 26, so on, $8,000. And each year after that, he deposited 7% more than the previous deposit. That tells us right away, this 7% tells us right away, this is a geometric series. It's going up by a percentage amount, not by a constant amount. So the second payment, or when he's 27, on his 27th birthday, he's going to put 8,000 times 1.07 in there, 7% more. And then on the next birthday, he'll put 7% more than that, so it'll be 8,000 times 1.07 squared. And then finally, on his 70th birthday, it'll be 8,000 times 1.07 to the what? This is 35 periods from here, so it'll be to the 34 power. Or we could just redo our scale here, and this will be the first payment, 8,000 at time, and then 8,000 times 1.07 to the 1 power, 8,000 times 1.07, 8,000 times 1.07 squared, and then finally this will be 8,000 times 1.07 to the 34th power. Once we understand that it's a geometric series, a geometric gradient series, we're going to use the formulas or the app on your calculator, however you're going to do it. I always use the app because that's the quickest way to get much quicker than looking into tables, or this app is really great. Okay, so the series starts with A1 equal to 8,000 and is increasing at the rate of 7%, so G is equal to 7%. By the way, whenever I pose a problem and then I start giving the solution is usually in blue, whereas the problem is in black ink, just like the rest of the course or the notes. And the account is earning at the rate of 5%. So not only is he depositing 7% more each period, but he's earning interest on this retirement account at the rate of 5%. And there are 35 deposits. So from the equation above, we have F equals, we're asked for, by the way, up here, what's the future value? How much does he have in the account right here when he's 70 years old? So it's asking what is F? And it's a big number. F equals how much? Okay? Well, this is the formula for the future value of a geometric gradient series. We had that previously right here. And I is unequal to G because G was 7% and I is 5%. So that's the formula we're going to use. Again, you could do this by just calculating, and you get $2,064,226. And I also did it on my cell phone. Now let's see if we actually can get that on the cell phone. So I go to my app and I push this back button to get back to, whoops, I push the back button to get back to the, and I don't have an F given G, given G1. Oh yes I do, I'm sorry, it's right there at the very bottom. I have a P given G and an F given G. I don't have an A given G. So I will just press that, and now it's asking me what's the interest rate. So I'll put in 5% or just 5, and then it's asking me for the growth rate. By the way, the app uses the symbol J where we're using the symbol I. And the reason, we're using the symbol G, a little lowercase g, for a geometric gradient series. So where they're asking for J, we're going to put in G, the rate of change of the series. It's called the growth rate. Of course, if G was negative, it wouldn't be a growth rate, but it's assuming that most times it is positive, and that's 7. Then it's asking for the number of years, and that's 35. And then it's asking for the first term in the series. How much did he start? And that's 8,000. And I put all that in, scroll up, and say to calculate the future value. And it comes out $2,226.45, in fact. But we're going to leave the cents off. There is the value from the app. And the next section I will go into is section 2.4, which is where your cash flows are shifted. The example that I'm going to use of a shifted cash flow is one that says, given a uniform series of $800 starting at the end of year 4 and continuing for 5 payments. So here we have a uniform series starting at 800 at the end of year 4, and it continues for 5 payments. The interest rate is 10%. What is the present value and what is the value of the series at time 3? So the present value would be the value here at time 0, and the other thing is the value here at time 3. And this is a uniform series, it says. So that means there's a $800 payment at time 5, time 6, time 7, and time 8. Uniform series looks like that. And we want the value in part A here, and we want the value in part B here. Well, actually, we're going to solve part B first, because whenever we multiply a uniform series amount of A dollars times P given A, the value of P is always 1 year before the first payment in the uniform series. So we're going to get the value that we need in part B at time 3 just by applying our formula like we did in the last class. So it'll be a P3, and I subscripted it so I know where that P is equal to A, P given A, I-N, A is 800, P given A, 10% for 5 payments. So there's the 5 payments. We multiply that times this factor, 3.7908. This I looked up in the tables in the back of the book, and I got that product is 30. It should not be 30,000. It should be 3,000 because that is $800, not $8,000 like the last example. So this is 3,000 and $33 actually, $32.60. So I'm going to make it $3,033. And then if I look that up, I'm going to use my app to get it. This is the present value of a uniform series. So this is going to be, this is the third one down, P given A, click on that, and let's see what my data is. I have, for the interest rate is 10%, so I'll put in 10. And for the number of cash flows or payments, that's 5. So I'll put that in. And then for my annuity, the problem was I left in the 8,000, but I need to get that out of there and put in 800. And then I do calculate, and it brings me $3,032.62. So I just recorded that here as $3,033. I'm going to cross that out because that's not correct. It's $3,033, and that's what I get both from this calculation and from the app. So this number here is the value at time 3, because anytime you multiply a uniform series amount by P given A, you get a value of P that is 1 year before the first A. So this value right here, this present value, is 3033. And, or I could say it's 303 262, because that's actually the value, actually 63 cents. That's the value returned from the app. Either way, it's not going to make too much difference. Then to get the value here, we have to reorient. This value is a present value. This $3,033 is a present value relative to this series, because it's back here from the series. But relative to this time, it is a future. Relative to this time, this point in time is a future. So we're just going to multiply this times P given F to get it back to here. So this will be P given F. What's our interest rate? 10%. How many periods? Well, that's 3 periods. And we're going to get a present value at time 0. So that's what I'm doing on the next slide, except I use the 30,000. It should be 3,033. This should be 3,033. And therefore, I'm going to move this decimal place. This should be 2,278 $2,278. And that concludes this portion.